Hey, what's up YouTube? A while ago I made a video on baking a water simulation into a flipbook texture. A technique that comes with lots of constraints, but one that comes with several benefits as well. And when I first started experimenting with this technique, I wondered if I could come up with a cheap buoyancy system. Here's my thought process. This texture tiles on the flipbook loops continuously, so there's no need to perform any computations at runtime to evaluate the wave height, right? Waves are not dynamically generated, they are baked. Thus, a single texture sample is the only step required to get the wave height. Now, a texture sample is processed on the GPU, while buoyancy is usually handled by physics on the CPU. Transferring data from the GPU to the CPU is possible, but it's usually a bit tricky to set up and can be quote-unquote costly. I've already made a video on building a custom buoyancy system using Niagara, so I've touched on this before. Niagara allows for easy data transfer from the GPU to the CPU, but still, what if we could avoid it entirely? My idea was to sample the texture ahead of time offline, bake the data into a format that's more CPU friendly and more compact, and then read it at runtime with minimal cost. Now, I implemented this in blueprints, so it's definitely not the most performant solution, but the underlying concept is sound. Keeping a copy of the data on the CPU side to avoid expensive GPU readbacks, when possible, is a common approach in game development. Of course, it's not without downsides. You have to think about the memory footprint and so forth. There are plenty of angles to this. Everything is a trade-off, as you know. Anyway, that was my idea at the time, and I gave it a go. I've had this project on my hard drive for a couple of years now, and I thought I'd make a video about it before trashing it. I'm not sure if it's going to be useful to any of you, but you never know. I'm just sharing. So let's take a look at how it works from a user's perspective, and then I'll do a quick technical breakdown. Let's assume I have a height map flipbook, one that I baked from a water FFT simulation like I demonstrated in a previous video. This flipbook is 8x8, meaning it has 64 frames in total. I can create a data asset and specify both the texture and the number of frames, 8x8. The frame step and resolution are there to, let's say, simplify the texture. Meaning, assuming I want to pre-sample that texture to drive buoyancy, I probably don't need per pixel accuracy, nor do I need to bake each individual frame. I likely can sample the texture at a lower precision and rely on pixel and frame interpolation to reconstruct an approximation of the displaced surface on the CPU and get a buoyancy simulation that works reasonably well. For instance, I could take 32x32 samples every 2 frames. Next, this setting means we are accounting for the oversampled pixels that are baked into the flipbook. Oversampling is here to address issues specific to tiling flipbooks, issues I covered in my FFT flipbook video. Once that data asset is created, I can right-click on it to bake the height data of this texture into a byte array. This array is very lightweight and can be accessed on the CPU. Speaking of CPU access, in any blueprint, I can use my sample flipbook blueprint library function. I specify the data asset I created and baked, and then set the samples to the world location, mapping size, amount of displacement, middle plane, time and frame rate. These settings must match those used in the material that samples the flipbook in the first place. This ensures that the CPU and GPU stay in sync. This function can also derive a normal, and these two settings control how the normal is computed. And that's pretty much it. The position this function outputs is the approximate position on the displaced water surface, and can then be used to drive physics forces like buoyancy. Alternatively, you can sample a few points and derive the best fitting plane. Then, using a simple spring interpolation, you can quote-unquote simulate buoyancy without physics. Quite cool. Now, I just want to reiterate that this is a Blueprint implementation and is by no means a performance solution. The cost, however, mostly comes from the virtual machine overhead, because of the very high amount of Blueprint nodes required to map a position in world space to several indices in that array to implement the time and spatial interpolation and smooth out the very sparse wave height data. It's nothing expensive per se, it's mostly simple math, so it'd be quite easy to convert this sample function to C++, and you'd see a massive performance boost. All these nodes would not translate to a lot of code, honestly. Blueprints do excel at certain things, but this kind of algorithm is clearly the worst case scenario for blueprints. But it gets the job done as a proof of concept. Alright, enough jibber jabber, let's dive into the technical details and see how it's built. Basically, there are three blueprints involved. The first is a blueprint function library that contains the sample flipbook function I just described. It contains quite a few nodes, and I rely on some helper functions as well, which I'll go over in just a moment. The second blueprint is an asset action utility, which exposes the bake and clear functions when right-clicking on the data asset. Finally, the third blueprint is the primary data asset blueprint, which essentially serves as a container for the settings and the baked values. Let's start with bake function, which presents the first challenge. Sampling textures on the CPU is highly inefficient, especially in blueprints. Unreal Engine includes a plugin that exposes texture sampling to blueprints, but it's extremely slow, so it's not a viable option. It also has a built-in function for reading individual pixels from a render target, but that's similarly slow, and reading many pixels one by one just isn't practical. Fortunately, UE provides a built-in function for reading pixels from an array of a render target, which is much more efficient. This is the function I'm going to use. But to do that, I first need to convert the flipbook texture into a render target. Here's how I do it. I first create a dynamic material instance using a simple material that just samples the texture to copy. For each selected asset, I ensure the flipbook is valid. Then I get the texture from the data asset, create a render target of the same size, and set the dynamic material's texture parameter to point to the data asset texture, the flipbook. Finally, I render that material into the render target, essentially copying the flipbook texture into the render target. Next, I calculate how many frames need to be baked based on the data asset's frame step setting. Then I pre-allocate the data asset's byte array, essentially creating an entry for each sample per frame. Here I simply calculate the frame resolution. For example, if I have a 2K by 2K flipbook containing 8 by 8 frames, each frame will be 256 by 256 pixels. Next, for each frame, I determine its X and Y indices, and then read the pixels within that frame. Oh, and I ensure the amount of pixels read matches the expected amount, just to be on the safe side. And this is where things start to get tricky. Let's assume each frame in the flipbook is 256 by 256 pixels, and I want to take 32 by 32 samples. Again, I likely don't need per pixel accuracy to drive buoyancy forces. Since this is a tiled flipbook, some samples overlap, meaning I can skip the last sample on each line, and skip the last line entirely as well. It's like I want to take 33 samples and then discard the last one, so I end up with 32 evenly spaced samples without any overlap. However, as we discussed in that FFT flipbook video of mine, each frame needs to be oversampled to address the tiling issues that occur with tiled flipbooks. So the actual area I'm interested in is a smaller region of each frame, and this depends on how many oversampled pixels were originally baked into the flipbook texture. Thus, the 32 by 32 samples need to be distributed within that smaller region. From here, I can compute how far apart these samples are in pixels. This is what I call the sample step. And that's exactly what I'm doing here. Next, for each sample along the y-axis, and for each sample along the x-axis, I calculate the sample's UV coordinates. And this is based on the sample step, the sample index, and the offset to account for the oversampled pixels I need to skip. From this UV, I can derive the 4 closest pixels to then do a bilinear interpolation in case the sample ends up in between pixels. That's what I'm doing here, and this is the usual process of mapping a 2D index to a linear index. So at this UV coordinate, I sample the 4 closest pixels from this frame's pixel buffer, and I do the bilinear interpolation. Once I have the final texture sample, I simply update the byte array. And then I repeat this process for every sample in every frame. When it's all done, I release the render target and update the dataasset array. And voila! This array now contains a list of all the texture samples in the following format. One row of samples one after the other, one frame after the other. So while this is technically a linear array, it actually sort of represents a 4-dimensional structure. A sample of index x and y in a frame of index x and y. Thus, knowing the number of samples per frame and the total number of frames, I can create some sort of mapping between this 4-dimensional structure and a linear index in this array. And that's where the sample flipbook function, part of this Blueprint function library, comes into play. This function's purpose is to allow the user to provide a data asset that contains the baked wave height data, and given a location, mapping size, time, frame rate, and a few other parameters, compute the position and normal on the water surface. So let's give it a look, shall we? First, I perform a couple of safety checks to ensure the provided data asset is valid and so on, nothing too important. Next, using the user-specified time and FPS parameters, along with the asset's frame step setting, I calculate a frame time. This means determining which flipbook frame the current game time corresponds to and how close we are to the next frame. Now, the values stored in the data asset array are in a 0 to 255 range, as it's a byte array. So I pre-compute a multiplier to remap these values to the user-specified range, the height input, which must match the value used in the material for the water surface displacement. Next, based on the size input, I calculate how far apart each sample is in centimeters. For example, if this frame is mapped to a 20 meters by 20 meters area in world space, and the dataset has 32 by 32 samples per frame, each sample will be spaced 62.5 centimeters apart. Still based on the size input, I compute a grid offset for this location. Assuming this point is the world space origin at 0, 0, 0, the grid index here would be 0, 0, minus 1, 0, 0, 0, 1, 0, you get the idea. Multiply this index by the grid size to get the grid offset. The grid offset is used to wrap the coordinates so that the sample location stays within the grid at index 0, 0, close to the world origin. It can then be converted to unit space based on the grid size, and from there to grid space based on the sample count. This gives me the grid cell X and Y indices, which correspond to the baked sample indices I'm looking for. From there, I find the 3 closest samples to create a quad. Finally, using the frame time I calculated earlier, I compute the current and next frame linear indices in the baked data array, and this is the mapping formula I showed just a minute ago. Next, I iterate over the 4 samples, and for each, I convert its x and y indices to a linear index, which is then added to the current and next frame linear indices to get 2 height samples from the array. I then perform a frame linear interpolation to get the final wave height. This, however, assumes the water level is at 0 in the z-axis. If that's not the case, you can simply add the water level to the z position here, no big deal. Oh, and I also reconstruct the sample's x and y position on the grid. Having computed the position of these 4 samples, I can then perform a bilinear interpolation to find the final position on the water surface at the desired sample location. And voila, assuming I don't need to compute a normal, that's the end of this function. Quite a process, right? But it's arguably nothing too crazy, it's mostly basic arithmetic. It's all about understanding how a world position can be mapped to x and y indices based on a certain grid size and grid cell count, and how these indices can be mapped to a linear index in an array. Now let's quickly go over the normal computation. I'll keep it brief because you could essentially repeat the same process I used for the height flipbook, but with a normal flipbook. You just need to use a vector array instead of a byte array to presample the wave normal. I, however, didn't do that. Instead, the normal is numerically computed from the wave height, and it can be done in 2 ways. The simplest method is to output a flat normal. This is similar to the flat shading in your DCC software, right? So first, I need a triangle to work with, and for now I have 4 vertices. Therefore, based on the normal triangulation mode, clockwise, counterclockwise, or best, which means the more distant vertex, I select the vertex to remove. Then, using the positions of the remaining 3 vertices, I compute the triangle's up vector, which, normalized, results in the triangle's normal vector. Quite simple. To get a smooth normal though, that's unfortunately a lot more involved and also quite expensive to do in blueprints. My idea was to use barycentric coordinates to compute a weighted average of the triangle's 3 vertices normals. And to compute a vertex normal, I believe the right approach is to average the surrounding triangle flat normals. This needs to be done 3 times, once for each vertex. It's nothing too complex nor interesting, so I'll be brief. This part here is about figuring out the barycentric coordinates of the sample location on our triangle. For each vertex we compute its normal, and that means averaging the flat normal of the 4 surrounding triangles, and it's pretty much the same process as before. A lot of 2D to 1D mapping, and lots of arithmetic. Definitely not ideal for performance in blueprints, but whatever. This is just a fun experiment. Once the vertex normals are computed, I do a weighted average using the barycentric coordinates, and that gives me the smooth normal. And voila, I'm pretty sure it's quite useless, but it was a fun exercise. And it works. Here's a test case with flat normals. Oh, and by the way, the flat normal could also be numerically derived from the wave position by sampling the position slightly to the left and slightly upward to compute the derivative. Similar to using absolute world position and ddx and ddy in a shader, right? Anyway, so that's flat normals, and that's smooth normals. It's pretty rough still, but the data set is tiny. The big data essentially corresponds to a 32 by 32 texture per frame, so not many pixels to work with. At least the memory footprint is tiny, only 65 kilobytes or so. Regarding performance, well, it's not great. Not because the approach is inherently flawed, but because, again, this is the absolute worst case scenario for blueprints. It's just simple arithmetic, but there are just too many nodes, and at this point the virtual machine overhead skyrockets. Sample a lot of points and it gets really costly. I was actually curious how a C++ implementation would perform, so I wrote one, and here are the results. This is the baseline. I'm being super lazy, this is a rough measurement in the editor, whatever. It's good enough to make my point. So this is the blueprint solution doing 100 samples. Ouch. And this is the C++ solution doing 100 samples as well. The difference is night and day. You go from something pretty much unusable to something that performs really well. But it's not just about performance. When using blueprints, you often have to jump through a lot of hoops for tech art, building editor tools and so on. It's just not what it's designed for. For example, getting access to a texture's pixel data. It's doable, but it involves so many annoying steps and it's unlikely to be performant. With C++, you simply get a pointer to the pixel data and that's it. See, this massive blueprint function translates to this small C++ function. When you're used to blueprints, as great as they are, diving into C++ opens the door to a whole new world, a whole new side of Unreal Engine. And it's definitely going to be one of my focuses in 2025. Converting BPs to C++, dispatching compute shaders in C++, and so on. I still have a lot to learn myself, and I have a few other projects to finish first, but it's coming. So stay tuned and subscribe. Great videos coming ahead. Voila, that's the end of the video. So what's the takeaway? Well, I'm not entirely sure. I guess the conclusion would be that when you send data to the GPU, data that you might need later on the CPU for gameplay, physics or anything else, the question of how to retrieve it comes up. Do we perform an asynchronous GPU readback, or do we keep a copy of the data in system memory? When the data is a texture, the latter can be done relatively easily in C++. The texture simply becomes a basic array. In Blueprints though, that's a different story. Blueprints are not really designed for what I demonstrated in this video. There are plenty of hoops to jump through, but still it can get the job done and works well enough as a proof of concept. Regardless of whether you use Blueprints or C++, keeping a copy of a texture on the CPU side only allows you to retrieve a single pixel value via a simple array lookup. And in the context of a flipbook texture, where you might want to implement downsizing and frame stepping in order to keep the data as lightweight as possible, plus pixel and frame interpolation, well, there are many additional steps to consider, just as I demonstrated in this video. Now, if your final thought is, well, this is irrelevant anyway, waves are dynamically generated now. Sure, Kerzner waves, FFT simulation, there are great ways to generate a dynamic water. Still, FFT flipbooks were used in some Assassin's Creed games, and even though Assassin's Creed 3 is quite old, I'd argue its water still holds up and might even look better than some recent titles that rely on procedural waves. So I wouldn't necessarily dismiss this solution. It may work for you or it may not, it's up to you. Everything in game development is a trade-off. It's all about weighing the pros and cons. Alright, that's it. Files are available as a tier 1 reward on my Patreon. Thanks for watching, I'll see you in the next video, take care of yourself, bye bye!